because probability creates the foundation for inferential statistics. Remember, inferential statistics is the branch of statistics where we take what we've learned about the small group and we apply it back to the large group. And so we use the probability or the likelihood that a particular event is going to occur to help us do that. So our topic, the next topic we're going to talk about is probability. And most people have kind of a basic understanding of probability, most times related to perhaps gambling, whether that's playing the lottery or doing some kind of cards, that sort of thing. But most people have kind of a basic understanding of probability, but probability in of itself is the likelihood or the chance that a particular event occurs. You know, we can talk about the probability of rain. That's the likelihood or the chance that it's going to rain today. And we can use that information that we get from the weather person or the weatherman, weather woman, whatever it may be, to make decisions about whether or not we're going to bring our umbrella in. You know, if the weatherman says there's a 30% chance of rain today, when I get here to the campus, I have to decide, well, should I bring my umbrella in from the car, or am I just going to not worry about it? And then there's the possibility that I could get wet walking to the car this afternoon because it's raining. So we make decisions, you know, do we have enough gas to get to school? Do we have enough gas in the car or the vehicle to get to school today? We use those probabilities almost every day on a daily basis to help us make decisions. Now, we don't go around thinking about it. You know, I don't go around thinking about, well, the weatherman said this, or, you know, I've got a quarter of a tank of gas. Is that enough? You know, we don't go around literally thinking about it and thinking about the probabilities and that sort of thing. But probability does govern a lot of the decisions that we make, even decisions that can be life-altering, like, should I accept a new job? We think about the pros and the cons and think about whether we think we would like that new job or not like the new job. You know, so we take all that into consideration, and that involves probability. So we're going to take a look at probability. Sorry. Oh, okay. Let me see what the problem is then. Now, okay, good deal. Sorry about that. I think I got it fixed now. Thank you for letting me know. Okay, so probability, again, is the likelihood or the chance that a particular event occurs. And it can be as something as simple as, for example, thinking about flipping a coin. And we can talk about the probability or the chance that we're going to flip a head, or rolling a die, a six-sided cube. What's the probability we're going to roll a 5? We can think about those. And it can be as simple as that. Okay? So there are 4 rules related to probability that kind of help us know that we're on the right track. Okay? So I want to talk about the 4 rules of probability. And it's going to be important for you to understand or know these rules, because these rules will help you to know whether or not you have the correct answer or whether you're on the right track. So these are the 4 basic rules of probability. The first one says that all probabilities are between and include 0 and 1. Okay, all probabilities, whatever you're thinking about, whether you're thinking about the probability of flipping a head on a coin, rolling a 5 on a die, drawing a red card out of a standard card deck of cards, whether or not Thanksgiving Day is on a Sunday, whether you have enough gas to get to work. All probabilities are between and include 0 and 1. So you can think about it, if you want to think about it like a number line, okay, you have 0 on the low end, and you have 1 on the high end, and then you have any fraction, any decimal value in between that. Okay, probabilities can be expressed as fractions, they can be expressed as decimals, and they can be expressed as probabilities, as, ooh, that went crazy, as percentages. Okay, so we can express them as fractions, decimals, or percentages. But the highest we would ever have is 1 or 100%, and the lowest we would ever have is 0 or 0%, which means, just as a side note, which means that probabilities are never, ever negative. You should never give a negative answer. I mean, it doesn't make sense to say there's a negative 30% chance of rain today, or there's a negative 50% chance I'm going to flip a head when I flip a coin. Okay, it doesn't make sense. So probabilities are never negative and are never greater than 1 or 100%. I know sometimes you'll hear people talk about, oh man, he gave 110%. Statistically, you can't give more than 100%. Okay? You can't give more than 100%. Rule number 2 kind of goes with this statement, okay, because rule number 2 tells us that the probability of 0 implies an impossible event. If the probability for a particular event is 0, that event is impossible. There's absolutely no way, no how that particular thing is ever going to happen. Okay? So if you think about our number line, at 0, we're saying that particular event is impossible. There's no way, no how it's going to happen. For example, the probability that we would roll a 7 on a die. A die is the 6-sided cube with the numbers 1, 2, 3, 4, 5, 6. There is not a 7. So there is absolutely no way in the world that you would ever roll a 7 on a die. So the probability of that particular event is 0. We could talk about the probability that Thanksgiving is on a Sunday. Is Thanksgiving on a Sunday? No. When is Thanksgiving? A Saturday? Nope. It's always on a Thursday. By law, It's always the fourth Thursday of November. Okay, so Thanksgiving is never going to be on a Sunday, at least in the United States. So the probability that Thanksgiving on a Sunday is 0. It ain't happening. Third rule, which gets us to the other extreme, says the probability of 1 implies a certain event, that the event is absolutely going to happen no matter what you do. It is certain to happen. Okay, you may want to say that, certain to happen. Okay, probability of 1, 100% chance that that event is going to happen. So that, again, thinking about our number line, that's on the other extreme. So at the other extreme, we have that our event is certain. And then, of course, we have any possibility in between that. The other one that I guess would be kind of most common or most familiar to you would be the one that's in the middle or halfway. That would be where we could talk about our 50-50 chance. So some examples for the probability that the event is certain to occur. If we said, what's the probability we roll a number less than 7 on a die? Well, if you think about it again, the die being a 6-sided cube, they're numbered 1, 2, 3, 4, 5, 6. And every number on the die is less than 7. So regardless of what number I roll, it's going to be less than 7. So this event would have a probability of 1. It's gonna happen. Another example might be, what's the probability that Easter is on a Sunday? What day is Easter on? Sunday. It's always on Sunday. Okay. So the probability that Easter is on a Sunday is 1 or 100%. So all probabilities are between 0 and 1, meaning it's never negative and it's never bigger than 1. If the value is exactly 0, the event is impossible, not going to happen. If the probability is 1, the event will definitely, without a doubt, happen. Now, the last one probably is not as obvious as you think it might be, or maybe it's not as easy to grasp, but it says the sum, which means you're going to add, of the probabilities of all options is 1 or 100. Okay, it says the sum, and the word sum implies that we're going to add them together. The sum of the probabilities of all the different options is 1. So let's think about it for a minute. If we roll a die, what things could happen when you roll a die? We could roll a 1, we could roll a 2, we could roll a 3, we could roll a 4, we could roll a 5, or we could roll a 6. And that's all the things that can happen when we roll a die. And if we think about the probability for each one of those, there's one way to get a roll of 1 out of the 6 options. There's one way to roll a 2 out of 6 options, one way to roll a 3, one way to roll a 4, one way to roll a 5, and one way to roll a 6. So the probability of each individual number is 1 out of 6. And what this property is saying is if I add all of those probabilities together, so if I add 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, it should equal to 1. Well, if you remember, to add fractions, you keep the denominator and you add the numerators. 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 is 5, plus 1 is 6. So we end up with 6 over 6, which simplifies to 1. Okay, so when you think of all the things that can happen, and you think about the individual probabilities, they're going to total to 1. Again, because the 1 implies something's going to happen. And when I roll a die, something's going to happen. I'm either going to roll a 1, a 2, a 3, a 4, 5, or 6. Now again, the intent of those rules, at least initially, are to help you when you're trying to answer questions related to probability, so that you know that you're at least in the ballpark, because you know you got to have a number between 0 and 1, which means it can't be negative and it can't be bigger than 1. So if you get an answer that's negative or you get an answer that's bigger than 1, then you kind of know you made a mistake. Now, sometimes probability questions can be basically just as straightforward as you want them to be. Okay, so for example, if we consider our event maybe is to flip a coin. Okay, so that's our event. That's what we're going to do. That's our experiment. Well, then we could talk about the probability that we flip a head. And guys, this is just a fancy notation in probability or in math and statistics. The P here stands for probability. Usually it's capitalized. The expression or the thing inside the parentheses here is what we would term a success. It's what we want. Now, there are lots of fancy-dancy formulas that are used in probability. But guys, probability is really very logical. If you'll just think about it, use your experience, and think about common sense what it would be. Okay, so if we're flipping a coin, okay, overall you usually think about the number of ways to get a success, and we divide it by the total number of outcomes or options. We divide it by the total number of things that could happen. Okay, that's the general, straightforward, here's how you figure a probability. Okay, so if we're thinking about the probability of a head, how many ways can you get a head on a coin? 1. And how many things total could happen? 2, because you're either going to get a head or a tail. That's 2 things. So the probability of a head is 1 out of 2. That's written as a fraction. It's okay. If we wanted to write it as a decimal, you could convert it, which would be 0.5, or to a percentage as 50%. Now, you don't have to state it all 3 ways for a question. Pay attention to why the question is worded. Or if it's multiple choice, do they give you the answers as fractions? Do they give you the answers as decimals or percentages? Sometimes it depends upon what you're talking about. So that can affect it. Okay. Let me think of another example. Again, we can think about something as simple as rolling a die, which is a 6-sided cube. And we could think about what's the probability that we're going to roll a 2. Okay, what's the probability we're going to roll a 2? How many ways could you roll a 2?
One way.
There's one way, and there's how many things that can happen? 6. So it would be 1 out of 6. What if I said, what's the probability you're going to roll an odd number? Okay, how many ways could you roll an odd number? There's 3 ways, because I could roll a 1, a 3, or a 5. So there are actually 3 things that could happen out of the 6 total, which is 3/6. We do want to simplify our fraction. Remember, anytime you deal with fractions, you want to simplify. So probability of odd would be 1/2. What if we said, what's the probability we want to roll a 1 or a 5? Okay, that's a new word, or. Typically within probability, when you see the word or, that usually implies we want to utilize the operation of addition. Okay, when you see the word or, you think about addition. So how many ways could we get a 1 or a 5? 2, because I'm either going to get the 1 or I'm going to get the 5. So there's 2 things that could happen out of our total of 6. Again, make sure you simplify your fraction to 1/3. Okay, I'm going to ask you a tricky question. What's the probability that you roll, let's say, a 3 and a 4? That's 0. In statistics, in this phrase, because we're only doing the event or doing the experiment one time, we're going to roll the die one time, and here means that you want both to occur at the same time. Well, you just pointed it out. We can't roll a 3 and a 4 at the same time. Not if we're only going to roll it one time. So the probability you are correct is 0. Because you cannot roll a 3 and a 4 at the same time. Okay, so sometimes they're really straightforward. But as you begin using probability in relationship to research, where you've collected your data, you may need, again, to organize your data, sort of like we did with our frequency distributions. But we use a special type of frequency distribution called a contingency table. Okay, so I want to talk for a minute about a contingency table, and then we're going to get into how to use those. Okay, a contingency table is sometimes called a two-way table. It's a special frequency distribution. Remember, frequency distribution is a fancy way to say table. So it's a special table, and it actually lets us look at the relationship between two qualitative variables. Okay, so we are going to kind of meander a little bit back into talking about qualitative data or qualitative variables, because a contingency table is a way to organize qualitative data. Perhaps you want to sort your data into groups. We could, let's see, what the example we used in class was the county of residence. So I could sort you into county of residences and perhaps gender. Or we could do gender and your pathway or your major. We could do pathway or major against your county of residence. Okay, so you're looking at the relationship between two qualitative variables. And so it's a special way to display it. So what happens, I'm going to see if I can sketch a rough sketch of one here for us so we can talk about it, is that we would have some of our information would be on each row. So for example, we might put the county of residence in our rows. So we might have things like Bartow, Cobb, Floyd, and you'd have them all listed. Okay, I'm just doing a rough one here. Okay, so you have some information on your vertical or on your each row, but then you also have information in each column. And maybe just for example's sake, we might divide by gender, biologically determined gender. So you're going to have male or female. And so you're going to have information in the columns as well. We also like to have, just to help us out, we like to total each row, and we like to total each column. And this corner right here, the lower right-hand corner, should match the grand total, which in terms of research would correspond to your sample size. I've got an extra column on my table, but it's okay. That's why it's called a two-way table, because you read some information off of the columns, you read other information off of the rows. And so if you think about how that all kind of comes together, okay, so for example, if I wanted to look at this particular sale, okay, and I'm just going to put a random number in there. I'm going to say 5. That tells me that there were 5 males living in Bartow County. That's what that means, okay? Because that number is in the column labeled male, and it's in the row for Bartow. So where the two intersect, so that was 5 males living in Bartow County. I bet you guys have seen these kind of tables before. You may not have known that they were called contingency tables or two-way tables, but I bet you've seen them before. Again, it takes the data and allows you, especially if it's qualitative, words and phrases, and to divide it up into various categories of your choosing. And we can then use the two primary uses of contingency tables is with probability theory, which is what we're talking about. But they're also used later on in one of our statistical analyses called the chi-square test for independence and homogeneity. Now, that's actually a topic that will be discussed in the next course. We're actually offering for the first time in spring a sequence to this course. Okay, we're focusing on bits and pieces, but there's going to be a second course. It'll be Math 2401 that will do a continuation. And so in that course, you'll get to talk about the use of contingency tables in relationship to what's called chi-square test of independence and homogeneity. For us, our focus is going to be on the probability, being able to read it and figure out the probability of a particular event. So we're going to take a look at some examples. Y'all ready? Okay, so I created, they're on the PowerPoint or on the, they're on the PowerPoint and the video that's in D2L, but I printed some off so we could work on them kind of individually one at a time, and I could show you how it works. Sometimes when you get these tables, sometimes they already have everything kind of totaled up for you, and then other times they don't. This particular two-way table represents the gender and the location of the residence for customers for a pizza delivery service. So say like Pizza Hut's going to deliver, and they want to kind of know where their customers live and whether they're males or females. So they've conducted a survey of customers, and these are the results. And they've organized it into a two-way table. If you'll notice, in each row, you have the residence, whether they live in an apartment, the dorm, with their parents, in a sorority or fraternity house, or somewhere else. And then on the horizontal, or in the columns, you have their gender. But they didn't total those things up for me. Okay, so one of the first things I would do, because it's going to make our lives a lot easier as you begin answering questions and thinking about it, is to have those totals. Guys, don't overthink it. Okay, you're just going to take your calculator, okay, and it doesn't matter whether you do rows or columns first, okay. So if I start adding, I would do 102 plus 115. That tells me there are 217 customers who live in an apartment. I'm then going to do 244 plus 157. Tells me there are 401 who live in the dorm. 240 plus 63, I'm going to do that one in my head, that's 303 that live with parents. 169 plus 200, that's 369 that live in a sorority or a frat house. And then 171 plus 124 is 295. Then I'm going to go back and I need to do the columns. Okay, so I would start, it doesn't matter where you do male or female first, so I'm going to do male. 102 plus 244 plus 63 plus 169 plus 171 gives me 749. And I'm going to do the other one, 115 plus 157 plus 240 plus 200 plus 124 gives me 836. Now, this number in the corner should correspond to my sample size. And it should be the same for the column and the row. So I'm going to double check myself. Let's see, 749 plus 836 is 1,585. I have 217 plus 401 plus 303 plus 369 plus 295. That's also 1585. At least they didn't make a mistake. You want to double check your rows and your columns because they should total to the same value. That's your grand total. Okay, so now we've got everything marked. And we can begin looking at our questions. And guys, sometimes the questions are very, very straightforward. Okay, so for example, if I ask you, what's the probability that the customer is a female? Well, using that same thought process that we had just a minute ago, although I'm having to read a table, how many ways could I get a female? If I'm going to choose a customer, one customer, how many ways could I get a female? 836, because if I look at, here's females, and if I look at the grand total, there are 836 options. 836 of those customers are female. Out of how many? Out of the total, 1585. Okay, so the probability of a female in this particular scenario is 836 over 1585. Now, you know, it's a fraction. We could leave it as a fraction, but we're probably going to convert it to a decimal. So we would do 836 divided by 1585. I believe you're asked to round to 3 places. So we would have 5, 2, 7. So if you wanted that as a percentage, that's about 52.7% of the customers of this pizza place are females. It's straightforward. It's a little bit more involved than flipping a coin or rolling a die, but it's the same process, the same thought process. Okay, let's do another one. Same table. I just already went ahead and totaled it up after we'd done it one time. Okay, what would be the probability that the customer lives in an apartment? Okay, how many ways could you get a customer that lives in the apartment or in an apartment? 217, very good. Okay, because here's apartment. Go over. There are 217 customers total that live in an apartment out of 1585. So again, you got 217 over 1585. We can change that to a decimal. 217 divided by 1585. What's your rounding? 0.137 when you go to 3 places. The 9 next to the 6 bumps it up. Or as a percent, you'd have 13.7%. Remember, to get from a decimal to a percent, you multiply by 100. And I'm doing that in my head. Again, reasonably straightforward, guys. Just don't overthink it. Okay, same table. Okay, this time let's do, I'm going to write it on here at the bottom. Probability that they live in the dorm or the sorority or frat house. Okay, probability they live in the dorm or the sorority or frat house. Okay, so I see the word or. So remember that that tells me that I need to add together. Okay, so we have dorm, and I have a total of 401 out of the total. I have sorority or frat house, which is 369 out of 1585. Could a person live in the dorm and a sorority fraternity house at the same time? in this scenario? Does a person live in the dorm and a sorority or frat house at the same time? No, because notice that that's two separate categories, so there's no overlap. That's good because I haven't double counted somebody. I don't want to double count you. Okay, so we add these together. Again, remember with fractions, keep your denominator and add the numerators. I'm going to get my calculator to do that. 401 plus 369 is 770. There's our fraction. I can convert it to a decimal. That would be 0.486, or as a percentage would be 48.6%. Now guys, it's really logical. I mean, there's fancy dancy formulas for this, but think through it, okay? If you have to draw, rough sketch you the table off and circle things like I'm doing, that will help you to kind of keep it straight. Okay, what about the probability that you have a male or they live in an apartment? Again, I notice I have that word or, so I'm probably going to add, okay? So let's think about it. I got males, so here's male. My total is 749. So I got 749 out of the 1585. Then I got apartment, which was 217 out of 1585. Anybody notice a problem? No. Well, but I could have a female that lives in an apartment and be okay, because I'm counting those who are male, just male, and I'm counting those who just live in an apartment. So a female could live in an apartment and I'd be okay. What about this right here? What's happened with this number right here? You double counted it, because I counted that 102 within the males, and I also counted it for living in the apartment, right? So if I double counted it, I'm going to subtract that amount off so that I only have it included one time. I don't want to double count it. Now, you could figure this out logically, okay? This is kind of the math formula here, okay, that I'm doing, because I counted all the males, I counted all the apartments, but I double counted. See, I had 102 included in this 749. And I also had 102 included in the 217. But I don't need to count it twice. So I'm going to take it off. Okay, so I'm going to use my calculator, and then I'll show you something. 749 plus the 217 minus 102. I get 864 out of 1585. I'm going up. As a decimal, that's 0.545. As a percentage, that would be 54.5%. Now, maybe your brain doesn't work that way, okay? But notice, what we could do, if your brain, maybe your brain works this way. I could say, well, okay, I've counted all the males, There's 749 males. Counted all the males. And then I realized, oh, I've already counted these males up here that live in an apartment. I just need to include the females that live in the apartment. So I could add 115, and I bet you money that I still get 864. Okay, so by drawing the lines and pictures and things in there, I hope it lets you see either that you've double counted or that you can just count the females that live in the apartment. Either way, you're going to get the right answer. Okay, but you got to think it through, guys, and it's going to help you if you'll draw the picture. I really don't want to give you the formal formulas because they get really messy. Okay, what if we said, what's the probability of a male who lives in the dorm? You can see it. Okay, probability of a male who lives in the dorm. Now this one may not be as obvious, okay, but this is like an and, because we want to have a male and we want him to live in the dorm. Okay, so let's look at it. Male, here's my males, and they live in the dorm. With and, I'm actually looking for that point of intersection. Where the two intersect or overlap is where they both occur. So I have 244 males that live in the dorm. Y'all with me? And that's out of the 1585. Out of my grand total. So doing my math, 244 divided by 1585, I get 0.154 as a decimal, or as a percentage, it'd be 15.4%. Okay, what would be the probability of a female who lives with parents? Parent or parents. Okay, again, it may not be overly obvious, but that's an and, because we want it to be a female and we want her to live with her parents. Okay, so looking at my table, here's my females, and we want her to live with her parents. So my overlap with the and, we're looking for the overlap, is 240. So I have 240 females who live with their parents out of my total of 1585. Convert it, 240 divided by 1585 is 0.151 or 15.1%. Okay, the last phrase that you're going to see, and it's kind of a different one, and it's a little bit trickier, is called given that. Okay, we want to know the probability that a customer lives in a sorority or frat house, given that it's a female. Okay? The probability that this customer lives in a sorority or a frat house, given that she's a female. Okay, here's what that means. Guys, we're given that. We know that we know that we know. Without a doubt, we have a female. So I can focus my attention on the females. I'm going to ignore the males. I'm going to ignore the totals because all I really care about are the females, because it tells me in the question, given that it's a female. Okay? So all I'm looking at is the females. I don't care about anybody else, at least in this question. Okay? So then we want to think about how many live in a sorority or a fraternity house. So sorority, fraternity house. There are 200 females living in a sorority or fraternity house out of how many? 836, because we only had 836 females. And we know that we got a female. So I ain't worried about the rest of them. Okay, so then we convert it, just like we've been doing. 200 divided by 836, 0.239, or 23.9%. Okay, anytime you see that phrase given that, you're going to narrow your search or narrow your list to just that thing, because you know that that's what you got. Okay, one more. It's getting hot in here. Okay, what's the probability that it is a male living, given that they're living in other? Okay, what's the probability that you have a male given that they're living in some other place? Okay. So again, in this scenario, because of that phrase given that, okay, they're given that they're living in other. So I'm going to focus on other. I'm not worried about any of the rest of the types of residences or even the totals. I'm going to focus just on those living in other, because we know that they live in other. So looking at my table, the number of males would be 171. So I have 171 males out of how many? 295 living in other. Again, you have to narrow your search. Okay, so we have 171 divided by 295, which would be, let's see, 0.580. What's your rounding? 58.0%. Questions? Guys, don't overthink it. It's very logical. And if you'll think through it, draw the circles and the X's and all that, I think you'll get it. Okay? Again, there's fancy dancy formulas, but I think they would be more confusing than anything else. Okay. One last thing. I've got about 19 minutes left. Let me see if I can do this.